Okay, so hello and welcome back. So in this video we will talk about a little bit about adjoint and inverse of a matrix. Adjoint and inverse of a matrix. And we are talking about matrices, not determinants, of course. So basically in the previous chapter we have studied inverse of a matrix. In this chapter, in this section, we shall discuss the condition for the existence of inverse of a matrix. So now let me go back to the previous chapter. Okay, so what we did in the previous chapter, there was a section called Invertible Matrices. Invertible matrices. And as a definition, we said that we had a definition in the previous chapter, which was if A is a square matrix of order M, and if there exists another square matrix B, and if there exists another square matrix and if there exists another square matrix B, another square matrix B of the same order M, such that AB is equal to BA is equal to I, then B is called the inverse of the matrix A. Then B is called the inverse of the matrix A, denoted by A inverse, or A inverse, using this notation. And in that case, of course, you can say that A is invertible. So for example, if you have for example two matrices, for example A is equal to, for example, this matrix 2, 3, 1 and 2, and you have another matrix B which is basically 2, negative 3, negative 1 and 2, and if you multiply A by B, that's going to be equal to B times A, which is equal to I, which is equal to basically 1, 0, 0, 1. And then you can say that B is equal to the inverse of A inverse, and also you can say that A is the same thing as the inverse of B. That's what we did in the previous chapter. And we also proved that basically the inverse of a matrix is unique, if it exists, is unique. We also said that if A and B are invertible matrices of the same order, then AB whole inverses, and those are basically different things that we so this is also interesting that we used in the previous chapter extensively. We said that if AB are invertible matrices of the same order, this was theorem 4 basically over there, although they have nothing to do with here, but if A and B are invertible matrices, of the same order, then A times B whole inverse is the same thing as B inverse times A inverse. D inverse times A inverse. And then we had a whole lot of things here to discuss, and we discussed them all. Now in this chapter, what we are going to do is that we are going to use the definition of adjoint and of the adjoint of a matrix in order to find the inverse of the matrix. Meaning that in the previous chapter, as you can remember, I was not very willing to do all of those row and column basically operations, because I knew that basically that was really not required. Since there is all of these, since there is a way to actually find the inverse of a matrix using the concept of adjoint. And so then you can basically, so you can say that now to find the inverse of a matrix A, to find the inverse of a matrix A, that is A inverse, we shall first define adjoint of a matrix. We shall first define the adjoint of a matrix. The adjoint of a matrix, right? Now, the adjoint of a matrix so as a definition number 3, we have the adjoint of a square matrix A is defined as the transpose of the matrix A, where basically A of ij is the cofactor of the element A of ij. The adjoint of the matrix A is denoted by adj of A. So then you can say that the adjoint of a square matrix A, which is equal to A of ij, and the order is, for example, n by n, is defined as the transpose of the matrix A of ij. The order is n by n, where A of ij is the cofactor of the element A of ij, is the cofactor of the element A of ij, meaning that basically for the matrix, you have to find the cofactor of each of those of each of the elements of the matrix. Then that gives you basically that gives you a new matrix. Then you take the transpose of that matrix, and the transpose of that matrix becomes the adjoint of the square matrix A, and which is denoted by ADJA. So you can say that the adjoint of the matrix A is denoted by ADJ, adjoint of A. This is the notation. So now let A be equal to some matrix, as for example A of 1 1, A of 1 2, A of 1 3, and A of 2 1, A of 2 2, A of 2 3, 2 1 2 2 2 3, A of 3 1, A of 3 2, A of 3 3. So let's consider this as the matrix A. And the adjoint of A is equal to the transpose of the matrix that you form, and take each of these elements and calculate the cofactor of that element. For example, this becomes A of 1 1, A of 1 2, A of 1 3, A of, for example, 2 1, A of 2 2, A of 2 3, and then you have basically A of 3 1, A of 3 2, A of 3 3, and that is the matrix that you get. And when you take the transpose of this matrix, you will have basically, you have to take each row and make a column out of each row, which gives you basically, for example, this row becomes one column here, so you get A of 1 1, and then you have A of 1 2, and then you have A of 1 3, and then you have A of 2 1, and then you have A of 2 2, and then you have A of 2 3, and then you have A of 3 1, and then you have A of 3 1, A of 3 2, and then you have A of 3 3, and that is basically a matrix that is the adjoint of A. So you have A of 1 1, A of 2 1, A of 3 1, A of 1 2, A of 2 2, A of 3 2, A of 1 3, A of 2 3, and A of 3 3, right? So pretty simple, but of course it does wonders for you, because then you don't have to go through all of those row and column operations. You can, of course, this is again some work, because you have to calculate the adjoint, the cofactor of each of these elements here, which is of course in effect basically the same thing as doing all of those rows and column operations, but then this is standard work, meaning that you don't have to think that much about what do I need to multiply by this or and so on. This is not so manual as in the case of basically the row and column operations. So now let's do an example here. Example number 23. We have to find the adjoint of A. You want to find the basically adjoint of A for A is equal to basically this matrix 2, 3, for example, 1, 4. Okay, so you want to find the adjoint of A for A is equal to this matrix, right? So first you need to find first you need to find the cofactors of these elements, which is basically you can say that, for example, the cofactor of this element 2 becomes A of, for example, 1, 1, and that is the same thing as basically negative 1 raised to the power 1 plus 1 times the minor of this element, which is deleting this row, deleting this column, you'll get a 4, right? And that gives you basically negative 1 to the second power is 1. 1 times 4 is equal to 4. The cofactor of the second element here is A of 1, 2, which is negative 1 raised to the power 1 plus 2 times, so deleting this row, this column, you'll get a 1 here, and negative 1 raised to the third power is negative 1, so you have negative 1 here. A of 2, 1 is the same thing as negative 1 raised to the 1, 2 plus 1 times, so the cofactor of 2, 1, deleting this row, this column, you'll get a 3 here, and negative 1 times 3 is equal to negative 3. And the cofactor of 2, 2, you'll get negative 1 raised to the power 2 plus 2 times the minor of the element A of 2, 2, which is basically 2 here, which is 2 here, so you have 1 times 2 is equal to 2. Then basically the adjoint of A, so then you can write the same matrix. You can write it as, for example, some matrix B, and write the cofactors that you found in the same order in this matrix B. I'm not saying that it's A, just some other matrix B, for example. So you have 4, for example, negative 1, and negative 3, and 2. That is basically, that is matrix B. And matrix B is basically you can say that the matrix B is basically this matrix, which is the cofactors of these elements here. So A of ij, for example, that you can say. And now the adjoint of A, the adj of A, is the transpose of basically, I don't remember what is B transpose. I think you can write it as B raised to the power T or something, some notation like that. And the transpose of B is equal to this matrix 4, negative 1, and negative 3, and 2. And that becomes the adjoint of A. 4, negative 3, negative 1, 2. And as a remark, you can say that for a square matrix of order 2 given by A of 1, 1, A of 1, 2, A of 2, 1, A of 2, 2, the adjoint A can also be obtained by interchanging A of 1, 1, A of 2, 2, and by changing signs of A of 1 to A of 2, 1. And we state the following theorem without proof. Okay. So basically it seems that calculating the adjoint of a matrix of order 2 is simple, and so we can find a rule for that. So let's see how we can do that. Now, in order to find, basically as a remark, you can say that to find the adjoint of the adjoint of a square matrix of order 2, we have so let's say that let A be for example this square matrix A of 1 1, A of 1 2, A of 2 1, A of 2 2. This is your square matrix of order 2. Now what we did was that we calculated the cofactors of each of these elements, right? So the cofactor of A of 1 1 is equal to basically negative 1 raised to the power 1 plus 1 times basically A of 2 2, which is equal to A of 2 2. Now A of 1 2 is equal to negative 1 raised to the power 1 plus 2 times the minor of A of 1 2, which is A of 2 1. A of 2 1, which is the same thing as negative A of 2 1, right? Now A of 2 1 is equal to negative 1 raised to the power 2 plus 1 times the minor of A of 2 1. This is A of 2 1. The minor of A of 2 1 is A of 1 2, which is equal to negative 1 times A of 1 2, which is A of 1 2, and the cofactor of A of 2 2, which is A of 2 2, capital A of 2 2, is equal to negative 1 raised to the power 2 plus 2 times A of 1 1, A of 1 1, which is equal to, well, A of 1 1. And then I write this matrix as, for example, some matrix B, and put all of the cofactors in here. So I write A of 2 2 in the same order, A of 2 2, negative A of 2 1, negative A of 1 2, and A of 1 1. And then if I take the transpose of this matrix B of t, B raised to the power t, actually not raised to the power, but this is the transpose of B, that would be basically the transpose of B, which is A of 2 2, negative A of 2 1, negative A of 1 2, and A of 1 1. And that is basically the transpose of B, which is the same thing as the adjoint of A. So the adjoint of, so if A is equal to A of 1 1 and A of 1 2, A of 2 1, A of 2 2, so you can see that you have these two elements have been swapped, meaning that instead of basically along the diagonal, you can swap these two elements, and then you can write the algebraic opposite of this element here and the algebraic opposite of this element here, and that would be how you would generally find the adjoint of a square matrix of order 2. So, and they have written it this way, meaning that they have written this as, if A is equal to the matrix A of 1 1, A of 1 2, A of 2 1, and A of 2 2, the adjoint of A is the same thing as basically the same elements if I write them in the same order. If A of 1 1, A of 2 2, and A of 1 2, A of 1 2, and A of 2 1. So along the diagonal you have interchange. They have written it as interchange, and along the other two elements that you can write, they have written sign change, which ultimately gives you, so if you interchange these two, you'll get A2 2, and over here you'll get A1 1, and sign change here you'll get negative A of 1 2, and sign change here, you'll get negative A of 2, 1. A of 2, 1. And that would be the transpose of the adjoint of your matrix. Okay, so that's basically the that is basically all about the adjoint of a matrix. And now we have a couple of theorems and a couple of definitions, actually a lot of them actually, and then we will go through the exercises. So now let's go through them one by one, starting from theorem 1. Okay, so now theorem number 1. Theorem number 1 we have basically if A is any given square matrix of order n, if A is any given matrix of order n, then basically A times adjoint of A times adjoint of A is the same thing as adjoint of A times A is the same thing as the determinant A times I, where I is the identity matrix of order n, where I is the identity matrix of order n. And for verification, so we can say that, for example, let A be equal to, for example, some matrix of order 3, for example, A of 1, 1, A of 1, 2, A of 1, 3, and A of 2, 1, A of 2, 2, A of 2, 3, A of 3, 1, A of 3, 2, A of 3, 3. And if that is A, so that's a square matrix of order 3, then the adjoint of A is A is basically taking the cofactors of these elements and then taking the transpose of those elements, meaning that you would get A of 1, 1, and then A of 2, 1, and then A of 3, 1. I'm sorry, A of not 2, 1, but A of basically 1, 1, A of 1, 2, and A of 1, 3, then A of 2, 1, A of 2, 2, and A of 2, 3, and A of 3, 1, A of 3, 2, A of 3, 3. So that would be basically the adjoint of A. Now, since sum of product of elements of a row or column with corresponding cofactors is equal to the basically determinant A and otherwise 0, we have let me see what this is. Okay, so now basically we said that for the verification of this, basically for the theorem 1 was basically if A is any given matrix of order n, then A times adjoint A is equal to adjoint A times A is equal to the basically the what do you call it, the determinant A times I. Okay, and now we want to prove it where I basically is the identity matrix of order n. Okay, now in order to prove this, basically what you have is basically there is basically they have written this very simple sentence here, but if you want to verify that sentence, it would probably take at least 30 minutes to do matrix multiplication, at least 15 minutes to do matrix multiplication in order to verify that. Let's see if we can do that. Okay, now if A is equal to this matrix A11, A12, A13, and so on and so forth, and then so the adjoint of A becomes this matrix here, and I have taken the cofactors of these elements, and then I have taken the transpose of those. I have written them in transpose order, meaning that A11, A12, A13, I have written this row has been written as a column. Again, this row has been written as a column, but the cofactors, this row has been written as a column, but the cofactors. Now this sentence is important, is of course a part of the verification or proof. Of course, these verifications, you can actually call them proofs because they are actual logical proofs, meaning that you can say that since the sum of the product of a row of the elements of a row or a column with corresponding cofactors with the corresponding cofactors is equal to basically determinant A and otherwise 0. I will tell you what that means. I'll tell you what that means. And otherwise 0, we have. So what this is saying is that since the sum of the product of the, so now you can put the sum aside and concentrate on the product of the elements of a row, the elements of a row multiplied by the corresponding cofactors. Where the corresponding cofactors is equal to basically to the determinant A and otherwise 0, meaning that we said that if you take, for example, in this particular case, if you want to calculate basically if you want to calculate the determinant A or basically determinant A written this way, if I call that, for example, delta, you can take this A11, for example, and multiply it by A of 11, and then add that to, for example, A12, and multiply it by the cofactor of the same element, and take the third element in the same row, A of 13 times A of 13. And you can do this for any row or any column that you want, and then you would get the value of the determinant of this matrix, because because if I write this matrix in the form of a determinant, if I write determinant A, that would be equal to, for example, this determinant A of 1, 1, A of 1, 2, A of 1, 3, A of 2, 1, A of 2, 2, A of 2, 3, A of 3, 1, A of 3, 2, A of 3, 3, and then basically normally what we do in order to calculate this determinant, we say that basically we expand this by, for example, if I were to expand this along the first row, I would say, for example, negative 1 raised to the power, for example, 2 times A of 1, 1 times, for example, the minor of A of 1, 1, which is basically this determinant here, for example. Let me call it, for example, the minor of 1, 1, and then I add to that, for example, negative 1 raised to the power, for example, 3 times, for example, A of 1, 2 times the minor of A of 1, 2, and add to that negative 1 raised to the power, for example, 4 times this element A of 1, 3 times the minor of A of 1, 3, which is m of 1, 3. Now this is basically the same thing, because the cofactor of, for example, the cofactor of or A of 1, 1 is basically the same thing as you can say that the cofactor of A of 1, 1 is the same thing as negative 1 raised to the power, for example, 1 plus 1 times the minor of the element, which is A of 1, 1, so m of 1, 1. And then if I write, for example, this part, I would have A of 1, 1 times negative 1 raised to the power 1 plus 1 times, for example, m of 1, 1. And as you can see, you have basically exactly the same thing here. A of 1, 1 times negative 1 raised to the power 2 times m of 1, 1, and so on and so forth, right? Now, and therefore, when we want to calculate the value of determinant A, what we can do is that we take we calculate the cofactor of the cofactors of these three elements, and then I write basically the determinant A is equal to the value of the determinant is going to be equal to, for example, A of 1, 1 times the cofactor of this element, which is A of 1, 1, and add to that A of 1, 2 times the cofactor of this, which is A of 1, 2, and A of 1, 3, for example, times the cofactor of that. So that's what we do there, right? Now, if I basically if I rewrite this part, which is basically A times adjoint A, for example, if I write A times, for example, adjoint A, what I will get is that basically you have this matrix times this matrix, right? So you have basically A11, for example, you have A12, A13, you have A21, for example, A22, A23, A31, A32, A33, and you have this matrix times this matrix, which is basically A of 1, 1, A of 2, 1, A of 3, 1, A of 1, 2, A of 2, 2, A of 3, 2, A of 1, 3, A of 2, 3, and A of 3, 3. Okay. Now, if you do this multiplication, you have to start with the first row and then go along the first column, second column, third column. And for example, you have the first row times the first. For example, if you do here you would get a 3 by 3 matrix, right? So a 3 by 3 matrix. Let's do the computation and see what we get. It's actually not that bad. So taking the first row and the first column, for example, and write it over here. So you have A11 times A of 11 plus A12 plus times basically A of 12, and you have A13 plus A13 times A of 13, right? So that is the first one. The second one would be this row times this column, for example. And as you can see, this is basically, now let me write this out, but then we will talk about the rest. So if I do this, if I multiply this row by this column, I will get A of 11 times A of 21 plus A of 12 times A of 22, and I will get A of 13 times A of 23. And then if I go for the third column, I will get A of 11 times A of 31. And then I have A of 12 times A of 32. And then I have A of 13 plus A of 13 times A of 33. Right, so that would be your matrix, right? And then now if you pay attention to this matrix, what you can see is that in this matrix I am taking A of 11 times A of 11, A of 12 times A of 12, A of 13 times A of 13. So that means that this is determinant A, right? This is the value of determinant A, because we calculate the value of determinant A in the exact same way. We take, for example, the row 1, for example, of this matrix, and multiply, for example, every element by the cofactor of the same element, and then add it to the next element times the cofactor of the same element, and then again take the next element times the cofactor of the same element, and that gives us the value of determinant A as we saw before. But over here what happens is that you have A of 11 times A of 21, you have A of 12 times A of 22, and you have A of 13 times A of 23, which means that this is absolutely zero, because we argued that, I don't remember where it was, but in a remark or in a note, we said that if we take the every element of a row or column, and then multiply it by the cofactor of the corresponding elements of another row or another column, the result is going to be zero, and we proved that, right? So that means that you will get a 0 over here, and you will get also a 0 over here, meaning that you get A of 11 times A of 31, A of 12 times A of 32, A of 13 times A of 33. Of course, these second A's are the cofactors of these three elements. But at the end of the day, you will have again a 0 over here. And so that means that basically you will get, this would be, this part over here would be the value of determinant A. This would be 0, this would be 0. then again you would get basically a 0 over here, the value of determinant A, and again a 0 over here. Again you would get 0, 0, and the value of determinant A if you do this multiplication. And therefore you can say that basically and that is actually the meaning of the sentence or the statement that we had here, that we said that basically the sum of the product of the elements of a row or column with the corresponding cofactors is equal to either the determinant A and otherwise 0, right? Which we saw how it functions. So then I can say that the A times adjoint A is the same thing as this matrix, which will give me a basic determinant A 0, 0, 0 determinant A 0, and 0, 0 determinant A, right? I would write these a little bit far to the right, and determinant A. And therefore, and I can take these out, meaning that I can take this is a matrix, not a determinant, so I can take the determinant A out, determinant A times basically, then you will get a matrix like is 1, 0, 0, 0, 1, 0, 0, 0, 1, and so as you can see, A adjoint A is equal to A times the determinant A times I, and so this is equal to determinant A times I. And similarly we can show that basically that adjoint A times A is again the same thing as basically the determinant A times I. And therefore we can say that A times adjoint A is the same thing as basically adjoint A times A, which is equal to determinant A times I. So we can say that A times adjoint A is equal to adjoint A times A is equal to determinant A times I. And this was basically this was theorem number 1. And so for theorem number 1, we showed that if A is any square matrix of order n, then A times adjoint A is equal to adjoint A times A is equal to determinant A times I, right? So that is basically the first theorem that we have here. Now, the second theorem that we have, we have a couple of definitions. Okay, so now let's go through a couple of definitions. So definition number 4, we have a square matrix A. A square matrix A is said to be singular, if the determinant of A is equal to 0. If determinant A is equal to 0. So if determinant A is equal to 0, then the square matrix A is singular. For example, you have the determinant of the matrix of matrix A. Matrix A is equal to, for example, 1, 2, 4, 8. 1, 2, 4, 8 is 0. Because if you write determinant A is equal to 1, 2, 4, 8, and that is equal to 8 minus 8, which is equal to 0, right? And so hence A is a singular matrix, is a singular matrix. Is a singular matrix. So that was all about this definition number 4 and a singular matrix. Definition 5. Definition 5. A square matrix A is said to be non-singular. A square matrix A is said to be non-singular if basically the determinant A is not equal to 0. For example, if A is equal to 1, 2, 3, and 4, then the determinant A is equal to basically 1, 2, 3, and 4, and that is equal to 4 minus 6, which is equal to negative 2, not equal to 0. And hence A is a non-singular matrix. And there are a couple of theorems that will be stated without proof. And those are theorem number 2. Theorem number 2. You have if A and B are non-singular matrices of the same order, if A and B are non-singular matrices of the same order, then AB and BA are also non-singular matrices of the same order. Then AB and BA are also non-singular matrices of the same order. And so theorem number 3, we have the determinant of the product of matrices is equal to the product of their respective determinants. The determinant of the product of matrices is equal to the product of is equal to the product of the determinants of the respective determinants of the respective determinants. That is basically the determinant AB is equal to the determinant A times determinant B, where A and B are square matrices of the same order. Where A and B are square matrices of the same order. And as a remark, we know that basically the adjoint of the matrix A times the matrix A is equal to the determinant A times I is equal to the matrix determinant A 0 0 0 determinant A 0 and 0 0 determinant A is equal to this matrix. We have had this before. Determinant of A not equal to 0, of course. Now, writing determinants of matrices on both sides, writing determinants of matrices on both sides. On both sides we have, so over here we had the adjoint A times A, that's two matrices multiplied together, so you can write the adjoint of A times A and take the determinant of that and take the determinant of this matrix as determinant A 0 0 0 determinant A 0 and 0 0 determinant A, and now based on what we said over here, we can write basically the determinant of adjoint A and A, we can write it as adjoint A and the determinant of that times the determinant of A is equal to basically this determinant on the right and then if we take the determinant A out from the three rows here, we will have basically the determinant of adjoint A times determinant A is equal to taking determinant A from the first row, the second row, and the third row. You have the determinant A whole cube and multiplied by basically 1 0 0 0 1 0 0 0 1 and of course when you multiply this determinant by basically by this determinant, you are going to get again the same, you're going to get the same value here, meaning that you'll get determinant A whole cube, and therefore you can say that basically the adjoint A times determinant A is equal to determinant A whole cube times 1, and well, actually what that means is that the value of this determinant is equal to 1, meaning that if you expand it, what you will get is that basically, for example, expanding along the first row, you would have, for example, negative 1 raised to the power 2 times 1 times this determinant, which is 1001, and then you would have this whole thing is 1, and this is 1 minus 0, which is equal to 1, so this whole thing becomes 1, and that's the one that we have written here, right? Now, so I can write basically determinant A and determinant, you can cancel out on both sides of this equation. You'll get the adjoint of A times is equal to the determinant A whole squared. So that is basically the determinant of adjoint of A is equal to the determinant A whole squared. So in general, if A is a square matrix of order n, so in general you can say that in general if A is a square matrix, of order n, then basically then basically the determinant of adjoint A, is equal to the determinant of A raised to the power n minus 1. So which means that basically, for example, meaning that, let me take a look at this. Okay, so here basically what this means is that, so here we said that basically the determinant of basically adjoint of A is equal to basically the determinant of A whole squared. And what that means is that, and here we said that basically in general, if A is a square matrix of order n, then the determinant of adjoint of A is equal to the determinant A raised to the power n minus 1, and that is basically in general, and that is, and you can see that here we were working with matrices of basically order 3, right? The square matrix of order 3, and we got 2 over here, meaning that if you take the order of the matrix as n, then the determinant A here, you get it as n minus 1. So, and it seems that it actually works that way if you work out all of the different, meaning that if you actually prove it. So that is basically, that was theorem number 3, and we are going to actually write all of these theorems, as we always do, in one place once we are done with all of the theorems. And so in the next video we have one more theorem and a couple of exercises. We will do that as well, and then we will basically start with the exercises related to this section. So I'll see you in the next video, and thank you.